A rocket, if we're being honest, is basically a flying oxygen tank. Because in order to burn its fuel at all, it has to carry all the oxygen it needs with it, in the form of tons of liquid oxygen. About 3/4 of the total fuel is just this oxygen. And now comes the idea that has haunted spaceflight for more than 40 years. Down in the atmosphere, oxygen is abundant. And it's free. What if an engine could simply breathe in this air, just like a jet, and only switch to its onboard tank once it's in space? A single engine gets you from a runway all the way to orbit. It's the most elegant idea in all of spaceflight. And at the same time, it's the idea that has driven one company after another into bankruptcy. Last year, it claimed its most famous victim. And yet, the engine at its heart refuses to die. My name is Serwan, and this is Mars Chronicles. Let's start with the problem that drives all of this. Why do we even do this to ourselves? A rocket carries two things, fuel and an oxidizer. So the oxygen for burning. There is no air in space, so it has to take both with it. But since the liquid oxygen makes up the lion's share of the weight, the gain would be huge if you could simply leave it out for the first part of the ascent. That's exactly the promise of air-breathing propulsion. As long as you fly low enough and slow enough, you breathe in the air from the atmosphere and skip the heavy tank. Only higher up, where the air gets too thin, do you switch to rocket propulsion. The result would not be a huge disposable tower, but a sleek, reusable space plane that takes off from the runway like a commercial jet. And this is exactly where the term "everything revolves around" today comes in. Single stage to orbit, or SSTO for short. In English, single stage to orbit. That means a vehicle reaches orbit without dropping a single part along the way. To understand why this is so incredibly difficult, you need to know the rocket equation. It says the required fuel increases exponentially with the target velocity. To reach low Earth orbit, you need about 9.4 kilometers s. A single rocket stage that wants to achieve this must therefore consist of more than 90% fuel. There's almost nothing left for structure, engines, and payload. Normal rockets cheat the equation by dropping stages, that is, empty tanks, along the way. But an SSTO vehicle refuses to do exactly that. Every kilogram of engine, tank, or wing comes directly out of the payload. On paper, SSTO is just barely possible. In practice, it's a knife-edge balancing act, and the air-breathing engine is the trick that might just make it workable. So let's take a look at the engines, because that's really the heart of this story. The first problem is speed. A classic jet engine with turbines only works up to about Mach 3, which is 3 times the speed of sound. After that, the incoming air becomes too hot and too fast for the sensitive blades. Then there's the ramjet, in German Staustrahltriebwerk. It doesn't have any moving parts at all and simply uses the vehicle's high speed to compress the air. It works from about Mach 3 to Mach 6, but there's a catch. It can't start from a standstill. It has to already be flying fast before it can even ignite. Even more extreme is the scramjet, where combustion takes place in air flowing at supersonic speeds. It's like trying to light a match in a hurricane. Such engines have only flown for a few minutes at a time so far. And now comes the ingenious solution that connects everything, the so-called Precooler. At Mach 5, the air flowing into the front of the engine is over 1000 degrees Celsius hot due to compression. The idea is to cool this scorching air down to about minus 150 degrees Celsius in 1/100th of a second.
Grad Celsius herunterzukühlen.
With the help of ice-cold liquid hydrogen. We'll take a look at how that works in just a moment. Suddenly, the air is cool enough that a regular turbine can compress it. This allows a single engine to breathe from a standstill on the runway all the way up to Mach 5. And after that, the air intake closes and it becomes a pure rocket. This Precooler is both the miracle and the curse of this entire technology. It's a heat exchanger that has to turn white-hot air icy cold almost instantly without freezing up or cracking under thermal stress. Remember this component. It's the secret main character of this story. This Precooler idea isn't new, and their history is a graveyard of failed dreams. It begins in Great Britain in the 1980s with a project called HOTAL, short for Horizontal Takeoff and Landing. That is, Horizontal Takeoff and Landing. That was a British spaceplane that was supposed to fly to orbit in a single stage. Its core was an engine called the RB 545. Nicknamed Swallow, that is, Swallow. It was designed by a brilliant engineer named Alan Bond. The rights were bought by the engine manufacturer Rolls-Royce. Also on board was the aviation company British Aerospace. The RB 545 was exactly that, a pre-cooled engine that breathed air up to about Mach 5 at an altitude of 26 kilometers and then switched to rocket mode. And now comes one of the most absurd episodes in the history of space travel. The engine was classified as a state secret by the British government and placed under the Official Secrets Act. So, the British law for the protection of state secrets. Alan Bond held the patent for his own engine, but he wasn't allowed to explain to anyone how it worked. This secrecy slowly strangled the project. It was nearly impossible to attract investors or partners that way. In 1988, the government pulled the plug, also because a sober calculation showed that the whole thing offered hardly any advantages compared to a conventionally built rocket. So what happened to the Rolls-Royce engine? The Schwalbe disappeared in 1988 as a classified matter, locked away in a drawer, without ever having flown. But its inventors did not give up. Alan Bond and two former Rolls-Royce engineers founded their own company in 1989, Reaction Engines. Because the old engine was classified, they had to design it completely from scratch. And they called the improved version Sabre. So that stands for Synergetic Air-Breathing Rocket Engine. So, Synergetic Air-Breathing Rocket Engine? The corresponding spaceplane was named Skylon. It was supposed to carry 17 tons into low Earth orbit. This company worked toward that dream for over 35 years. They raised over £150 million. Among others, the defense company BAE Systems acquired a 20% stake in 2015. Later, Boeing and a sovereign wealth fund from the United Arab Emirates joined in. And most importantly, they proved that the Precooler actually works. In tests, it cooled the incoming air exactly as planned in a fraction of a second. And then, despite everything, it was over. At the end of October 2024, Reaction Engines went bankrupt. In the end, the company was about £20 million short of being able to continue. Out of about 200 employees, 173 were laid off immediately. BAE Systems, Rolls-Royce, and Boeing all declined and did not save the company. By the way, Skylon itself never got beyond the concept stage. Development would have cost over $10 billion. The world's most famous company for air-breathing spaceplanes was history. And Great Britain was not alone in this dream, because there was also a particularly ambitious attempt in the German-speaking world that I must not leave out here, the Sanger project. It is named after Eugen Sanger, an Austrian space pioneer who studied in Graz and Vienna. In the 1980s and early 1990s, the German company MBB developed a two-stage spacecraft under this name. That is, one that flies into orbit in 2 stages. The idea was compelling. A huge air-breathing carrier stage with turbo ramjet engines was to take off horizontally from the runway and accelerate to about Mach 6 to 7. And at that altitude deploy a smaller rocket-powered upper stage called Horus, which would then continue alone into orbit. So instead of having a single engine handle both tasks, Sanger simply divided the work between 2 vehicles. In 1991, Europe's first turbo ramjet engine even ran on the ground. But in the mid-1990s that came to an end. They simply couldn't develop an engine that would have been efficient across the entire speed range. And in the end, the calculations showed only meager savings compared to the new Ariane 5 rocket. It was the same sober judgment as with HOTOL. In the United States, there was the path led to the same graveyard. In the 1980s, the government under Ronald Reagan announced the National Aerospace Plane Program with its planned X-30 aircraft, a scramjet-powered Orient Express that was supposed to fly into orbit in a single stage. In 1993, it was discontinued without ever having flown. In the 1990s, the X-33 from Lockheed Martin followed, a technology demonstrator for the large Venture Star spaceplane, featuring an exotic aerospike engine and carbon fiber tanks. After about $1.3 billion had been spent, it was also cancelled in 2001 after the innovative hydrogen tank failed during a test. But there were also bright spots, like the DCX Delta Clipper from McDonnell Douglas, a small rocket that took off vertically and landed vertically, showing years before SpaceX that it was possible. But the pattern remained. Every single major national SSTO program was cancelled before it reached orbit. Now let me give you my honest assessment, and I want to clearly label this as my opinion. Why does this dream keep dying over and over again? The cruel math behind it is simple. Even with a working air-breathing engine, you still end up hauling 2 complete propulsion systems up with you. Add to that wings, a heat shield, and the heavy precooler. All this extra weight eats up exactly the savings you hope to get by not carrying oxygen. That's exactly what the HOTOL calculation showed back in 1988. And while the engineers were struggling with this elegant solution, SpaceX simply went with the inelegant approach. They kept the stages but made them reusable. The Falcon 9 landed back, and Starship is supposed to become fully reusable. Elon Musk has publicly argued several times that a reusable 2-stage rocket is always superior to a single-stage one, because a true SSTO would hardly have any payload left. The brute force ugly solution has beaten the elegant one. And that's exactly why the SSTO spaceplane has lost its urgency. Because reusable rockets already provide cheap, repeatable access to space today. And yet, and this is the best part, the Precooler refuses to die. Because the idea is simply too good to bury. It's experiencing a revival in several places right now. The first is called Invictus. In July 2025, the European Space Agency ESA and the British company Fraser-Nash launched this program. They are using, of all things, the Precooler technology from the Bankrupt reaction engines and building a reusable test aircraft with it, which is supposed to fly at Mach 5 using hydrogen and exactly this pre-cooled air-breathing engine. Many of the engineers from back then are back on board. Important for context, Invictus is not aiming directly for orbit, but is first and foremost an honest first step. A Mach 5 demonstrator with dual use for civil aviation and defense. The preliminary design is expected to be ready within 12 months, so shortly after this video is released. The second revival comes from a completely different direction, and you already know it from our video. The company Liebherr 71 or Liebherr Lieb 71, led by Lynn Kaiser and Josephine Lissner, showed something amazing in November 2025. A 1.5 meter high precooler, not constructed by hand, but designed by their software neuron using computational engineering and then printed in metal as a single piece. At Mach 5, the incoming air reaches several thousand Kelvin. And to control this heat, the software uses a fractal folding structure to fit a huge cooling surface into the smallest space. It's exactly the old Sabre idea, but reborn through artificial intelligence and 3D printing. Maybe this way the Precooler will finally become affordable and buildable. And there's a completely different solution, which you already know from another one of our videos. Specifically detonation. Instead of pre-cooling a turbine engine, Venus Aerospace combines a rotating detonation rocket engine, or RDRE for short, with a ramjet engine. In May 2025, they completed the first US flight test of such a detonation engine. Their goal is a single engine that can operate from the runway all the way up to Mach 6. For a supersonic passenger aircraft called Stargazer M4, The American company Hermes is taking a similar approach, placing a precooler in front of a conventional jet engine and using a controlled dive to bridge the gap until their ramjet engine ignites. Also aiming for Mach 5? Even the dream of reaching space from the runway lives on, just not in the way we imagined. The New Zealand company Dawn Aerospace is already flying its Aurora, a rocket-powered plane that takes off from the runway like a jet. In November 2024, it broke the sound barrier and can fly several times in the same day. Significantly, however, even they do not rely on an air-breathing SSTO for reaching true orbit, but instead use rockets and ultimately 2 stages. My conclusion, the purely air-breathing single-stage spacecraft that goes from the runway all the way into orbit may never exist. The rocket equation and SpaceX with its reusable rockets have probably settled this question for now. But the engine at its heart, the precooler, this component that ends both fire and ice at the same time, stubbornly refuses to die. It has only changed its dream. Away from orbit towards mastering the hypersonic middle ground. Whether through the European Invictus, heat exchangers printed by AI, or detonation ramjet engines, the idea of an engine that inhales the sky is very much alive. Sometimes in technology, the most beautiful idea is also the most persistent. My name is Serwan, and that was Mars Chronicles. Thank you for tuning in, per Aspera ad Astra.